Welcome back, ladies and gentlemen. Here in this video, we're going to be trying to bring some knowledge together that's going to lead us into this huge idea that I know you've heard before. It's called the conservation of energy, but we're not there yet, technically. So without further ado, here we go. Get ready to get your math on. Here we go. So first, I want to start by looking at a situation where basically you just lift a box off the ground and you apply a force to it, and you're going to get the box up to this height. There's your force. And you're going to lift it through, let's say I'm lifting it, force of me. And you can lift it up to height h. Through that distance h, that's a vertical measurement of distance. What about the work you do? It looks like you do positive work on it. So, work done by me. I've got force of me times, well, typically distance, and then cosine angle, theta between that. Well, the force of me is easy. I have to overcome gravity. So, gravity's also acting on it. Weight. So the force of me is really equal to mg. The distance I'm lifting is height h. And theta, well, theta is 0 between my force and that distance. And so cosine of 0 would just be 1. So there it is. There's the work that I do. Work done by me. Okay. And that's going to be a positive value. Well, while that's happening, gravity is also doing work. So, how about the work done by gravity? Well, what's going on here? We start out force times distance times cosine of an angle. And the force, well, that's, again, mg. And the distance is still h. But this time, the angle between the force and the distance is 180 degrees. So cosine of 180 is -1. So I get this minus mg. Work done by gravity is minus. It's negative. Okay. So what about the total work done? Well, it's the sum of all the other work. So it's equal to work by me plus work by gravity. Okay. So the work by me was mgh. The work by gravity was minus mgh. Okay, well, that's clearly 0. The total work was 0 joules. And so what that means, therefore, what's the change in kinetic energy of the box? Well, when I get it up there, it has 0 velocity. When it started, it had 0 velocity. And by definition, total work is equal to the change in kinetic energy. So we have a 0 change in kinetic energy. Okay, so that's easy to see. Because of the two forces acting at the same time, 0 total work was done. Although each force, each individual force, was doing work. All right, well, question for you. What if, after lifting it and getting it up there, I let go? There's my box, and I let go of it. What's going to happen? It's going to fall to the ground, boom, and it's going to gain kinetic energy from the positive work done by gravity at that point. So look at that. All right. So if I let it go, well, then the work done by gravity is now okay, well, it's traveling that direction, and the force is in that direction. I'll get a positive amount of work done, which is really cool. And it's just going to be equivalent to mgh, in this case, on the trip down, right? And so, but that amount of work done, when it's falling, I'm not doing any work, so that's going to equal the total work done, isn't it? Well, and that's going to equal whatever change in kinetic energy you're going to get. We need to look at that a little more closely, don't we? What happens, though, is you end up recovering that energy. You put work into it and you let it go, and you're going to get energy back out of it. You recover it as kinetic energy. That's very, very important. If you can recover the energy, it must have been stored in the first place. So that's what we call potential energy. So up here, it had what we call potential energy. Stored energy. How did it get stored there? It got stored there by the work that was done, and not so much the work I did necessarily, although I guess it is equivalent to it. But the stored energy came from the work done by gravity, essentially, right there. Because what we're able to do is use gravity to recover that energy and get it back out as a kinetic energy. So let's look at that in some detail. Here we go. This is going to be intense. Are you ready? We're going to look at that situation first. Split screen. How about that? So what's the deal? We're going to say that this object, and I'm going to lift it. So force of me. While that's happening, gravity's acting on it. Put an arrow so we don't confuse all the W's that are happening around this place. And I'm going to lift it up to this position. And up in this position, well, I still have my force of me. And I still have gravity. But I've moved it through that distance h. And, okay, well, now this time I'm going to set it down. Okay, so this is my setting it down situation. And so it's going to, now looking at the reverse of this process, it starts here, and there are two forces acting on it. Force of me, gravity, and it's going to move through that distance h and end up there. And down here, still got gravity and still got force of me. Okay. So I set it down. Now, we need to look at this in totality. So what's going on? The work done by me. Through the whole situation. Notice that this block ended up and then back down. Where it ended up where it started, and that's very important to realize here. So the work done by me, okay, well, I've got my force times that distance, and but my force is equal to the weight, so work done by me is mg times h, and that's positive on the trip up. Now what about the work done by me on the trip down? There's the force of me, and there's the distance h. So my force is still mg, but now the angle between the two is 180, so it's a negative mgh this time. So the work done by me, overall, I do zero work overall from up to down to end up back where I started. Okay. What about gravity? Work done by gravity. Well, gravity is pulling down, it moves up, so this is going to be a negative mg, h. And we are adding on the trip down, they're in the same direction, so it's going to be a positive mgh. Okay, well, guess what? Gravity does zero work on the way down as well. Or overall, I should say. Overall. Remember, trip up and back. We're ending up back where we started. So how about the total work? Well, we have to add these together. Work total. Okay, it's going to equal, what is, well, work total, we know, is equal to change in kinetic energy. But what is the work total? The work total is work of me plus work by gravity. Change in kinetic energy is, well, there's no change in velocity. It has zero velocity in the beginning, zero velocity at the end, zero velocity at the top, zero velocity everywhere, except for the trip in between. So there is, there was no change in the kinetic energy, so everything just kind of zeroes out. 0 plus 0, confirmed, equals 0. Okay, we're done with that situation, with setting it back down. But let's analyze now letting it drop. Okay. So similar beginning. We're going to lift this thing up to height h. Same two forces, force of me. Notation, get my notation right. Weight is that force, and same two forces are acting up here. Force of me, weight with an arrow. And this time, however, okay, from this position, I'm going to let it drop. It's going to move through distance h in that direction. If I let it drop, well, what are the forces acting on it? Just gravity. No longer am I doing anything to it. That distinction, that difference right there to there is really, really profound. We got to see what's going to happen here. Okay, so we got weight there too. Same kind of analysis, work done by me. Is on the trip up is going to be mgh, but no, and that's positive. But I do no work when the block comes back down. So this is it. That's my work done. How about the work done by gravity? And so, you know, before we get to the gravity work, you notice right away there's a difference. I don't do zero work. I've done some work on it. Okay. Work done by gravity? All right. Well, we have on the trip up, it's doing minus mgh. On the trip down, it's doing plus mgh. Overall, work, the gravity does zero work. Well, again, we're going to find the total. Add these together. And the work total equals a change in kinetic energy. So this is interesting. The work total now is no longer zero. It's because we had the work by me and the work by gravity. And this is a change in kinetic energy. Well, delta K is a final minus initial kinetic energy. Okay, so why am I bothering to break it up like that? Because I know that this left-hand side is not equal to 0. So the right-hand side can't be 0 either. All right, so work done by me. Well, I found that was positive mgh. Work done by gravity was 0. Okay, well, so, what about kinetic energy? Well, kinetic energy is 1/2 mv squared. In this case, it'll be final velocity squared, and I'm taking away initial. 1/2 mv initial squared. All right. Well, so look at what's going on here. My initial kinetic energy at the top, considering the change in kinetic energy here, is well, 0, because I had 0 initial velocity at the top. And so that kind of goes away. Let me use a thinner pen here. So that term, is that right? No, yes, that's right. That's right. Gather my thoughts here. My initial velocity at the top was 0. Okay. So what ends up happening is I've got mgh equals 1/2 mv final squared. Notice something else. M cancels. It seems to be independent of the mass of the object. And so what I can do, what this allows me to do, well, I could rearrange and solve this for anything, but typically you're going to be looking for that final velocity. I mean, right before it hits the ground, boom, it's got that final velocity. It's got that from the final kinetic energy. And so if we rearrange for final velocity, well, we basically get this step in the middle, 2gh, and so square root everything. 2GH. Now, this guy right here might look a little familiar to you. Maybe. It's not an equation you really need to memorize. It's an easy equation to get now if you ever need it. That might look a little bit like times acceleration times change in position. And we get that from kinematics. Well, it's really the same equation. So this is an interesting thing. Little g is the acceleration, h is the distance traveled, so delta x in this case is in the y direction, but never mind that. We're now working with work and energy, but it totally, 100% jives with what we have already learned from kinematics. So that's kind of cool. Now, what is really happening here? In this situation, when we let it drop, the total work done, this business right here, the total work done, which is really the work done by me plus the work done by gravity, the fact that that's non-zero meant that there had to be a change in kinetic energy. And what that means is when we look at the situation from top to bottom, remember, we are starting at the bottom and up and then ending at the bottom. Then what happened was we recovered that energy back out as kinetic energy. We recovered that as a velocity, which is real close cousins to kinetic energies. One indicates the other. Okay, so that's what's happening with gravity. We let it go, we let it drop, and we recover energy out of it. We're going to contrast that with friction. Next. Paper's curled, it's making weird things happen. Contrast what we just saw with friction. Okay, so different situation. I've got a box I will slide across the floor. In order to do that, I have to apply a force to it. Force of me. That's going to get over here. And while I'm sliding it, there's friction. So there will be kinetic friction opposing the motion. Okay, fair enough. And it's going to go this far, distance x. So from there, and remember, I'm going to compare the two situations equally. And so I'm going to look at what happens when I take it one direction and then have to go back the other direction, right? So this is an interesting thing. Now I know I'll finish labeling my forces here. It's kinetic friction right there. So I'm going to get it back there. In this case, I'll just call that distance x. And now, to get it back, I have to reverse the direction of my force, don't I? So this is now force of me, and that's now friction, kinetic. Force of me and friction, kinetic. So, just like before, oops, we're going to push it there, and we're doing work one way, and friction's doing work the other way, and then we're going to push it back. And we're going to end up where we started. And let's look at this whole situation. So, this is kind of like stage 1 and stage 2. So, stage 1, work done by me. What's going on? Well, there's FD cosine theta. And, well, you know what I can probably do? I can probably combine stage 1 and 2 into a single line here. So let me get rid of that, because that's my stage 1 work, and I'm going to add my stage 2 work. That will be FD cosine theta, won't it? And so, how much work am I doing? How much force am I applying? I have to overcome the kinetic friction. And the kinetic friction work done by me. Kinetic friction force is coefficient of kinetic friction times, so let me write this down here. That's going to be equal to coefficient of kinetic friction times normal force. Well, what's the normal force? Normal force is mg, coefficient of kinetic friction times mg. There's my friction force, and I simply have to overcome that to get this box to this new location. So that's my force, is mu mg. Cosine of, not cosine, sorry, coefficient, kinetic, times m times g. That's just my force. Now my distance will be x, and cosine of theta. Well, my force and the distance are parallel. They're in the same direction. In the same direction is the more important characteristic. And so the angle is 0, cosine of 0 is 1. So there's my work done in phase 1. And in phase 2, my force is still mu mg, and distance is still x, and they're in the same direction. So this is still mu mg times distance x. So this is still just from there to there is still force, and there's my distance, and the angle is 0. So cosine of 0 is 1. There's my force on the trip back, and distance x, and so I'm doing positive work in both situations. It sounds weird, even though because direction change like that, direction change, right? But I'm doing positive work in each case. So what is the work done by me overall for both phases, for getting it there and back again? Well, that's just 2 times this business. Coefficient of kinetic friction, mgx. Okay, we're going to come back to this equation. Let's work out the work done by friction now. Okay, work done by the friction force. So let's separate this a little bit. Well, we have FD cosine theta, and that's during phase 1, and then we're going to add the work done during phase 2 by friction. So we have F d cosine theta. Now, what is the force? Well, we worked that out already. The force is mu k times, excuse me, mu k times mass times gravity. That's the force of friction. The distance traveled will be x. Now, this is interesting. Think about this now. Here's friction in that direction, but here's the distance in this direction. They're opposite, so they're 180 degrees apart. And that means cosine of 180 will be -1. So this gets a minus sign in front of it. Now, it's very important that I remember that. But the same thing is going on here. In phase 2, friction is to the right, but the distance travels to the left. Cosine is still 180, or I'm sorry, angle is still 180. So I'm going to end up with coefficient, mass times gravity, and cosine of 180 is still -1. Work done by friction is -2 times coefficient times mass times gravity. Oops, I forgot an x. Sorry. Times the distance traveled. So there's the work done by me and the work done by friction. And look, they basically are identical, right? So what's the total work? Okay, well, this is easy to figure out. Just add them together. We got work done by me plus work done by friction. So total work, well, work done by me is 2 coefficient mgx, and work done by friction is -2 coefficient mgx. Okay. Craziness. The total work done is 0. Well, was that surprising? That shouldn't be surprising. Not at all. This box started here with no kinetic energy, pushed it there, pushed it back, ended up with no kinetic energy. Okay, so therefore change in kinetic energy equals 0. That's not surprising at all. So what is different though? I mean, because we're contrasting this with what happened with gravity. Imagine this. If I push it halfway, so I push it over there halfway, and I let it go. It stays there. There's no recovery of stored energy. It's not going to all on its own go back there the way it did with gravity. With gravity, I push it up, and I let go. It's going to all on its own. All on its own, I recover that energy. Here, I push it over, and I don't recover that energy. There's no stored energy to recover. That energy was robbed. It was stolen, in fact. Thieves. What was the thief? What was the culprit? The culprit was friction. What the friction did was it robbed energy of the system, essentially, preventing it from getting stored in any way. And so where did that energy go? Well, the energy is almost entirely converted into heat. A little bit of sound, probably, but mostly heat. And at that point, it's useless energy. You cannot make use of that. And the study of that kind of physics, thermodynamics and entropy and all kinds of weird stuff, oh, that gets really interesting. But that's for actually another course. Don't have to worry about that right now. So very, very crazy that you can store energy with gravity, but you cannot store energy with friction, not directly. So what is this telling us? I got to wrap this video up. It's already going on long enough. So this is telling us that some forces conserve, that's an important word, some forces conserve energy and let you recover it as kinetic energy later. Other forces rob the energy, never to be seen again, never to be useful again. If a force conserves it, well, what do we call that? We call that a conservative force. Not too terribly imaginative, maybe. Conservative forces. So here's one way of defining what a conservative force does. Does zero total work on any closed path. What do I mean by a closed path? Starting and stopping at the same place. Well, that's what we did with gravity, right? We started at the bottom and ended up at the bottom. Same thing in setting it down, essentially, too. And we did the same with friction as well. So we started here and ended there. But there is a significant difference here, okay? A conservative force does zero total work on any closed path. All right. Gravity. In both cases, the work done by gravity did zero work. That force by itself, the force of gravity by itself, did zero total work on this closed path here. Look at friction. Friction, all by itself, going there and back, did not do zero total work. It did not conserve the energy. It did not save it. It did not store it. And that's significant. Okay, so on a closed path where we end up where we started. So that's a conservative force. Well, a non-conservative force does work on a closed path. The total work by that force would not be zero. Some examples, real quick, of conservative forces. You already know one, gravity. There's two important ones. Gravity, paper shifting, come on, hold still. There's another one that we will use a lot, spring force. Is a conservative force. How about non-conservative forces? To wrap this up, okay. Non-conservative forces. Well, you already know one. It's a real important one. Do not ignore it, but know what to do about it. Friction, non-conservative. There's another interesting one. Tension, like in a string or rope. is not a conservative force. And there's others, but we don't have to really worry about them right now. Okay. Wow. So this is sort of a very important, I would call this a very important analysis of different situations. A lot of math that we had to look at, but you certainly don't have to memorize it all. You could derive all this, again, anytime you needed to, as long as you understand how to apply forces and calculate the work done by each individual force. Then you're going to be okay. Thanks for watching. I'll catch you next time.